Okay, so let's say we have a system like this. X plus 2y equals 4 and 2x plus 5y equals 9. Okay, well, you might have seen a system like this in an algebra course in which you thought of it as two equations and two variables, and your solution method might have been solve the second equation for x in terms of y, and then plug in for x up here. Then you have equation one variable and solve for that. And we're not going to do that. So we're going to use what's called Gauss's method, in which we're going to put this in the standard form in which we have a linear combination on the left, the equal signs here, and the constants on the right lined up, and our variables will always be lined up. And we're never going to make certain moves that you could make algebraically, like we're never going to switch 2y plus x. We're going to always keep the columns in x and the columns in y, and they'll always be there. We won't switch them left and right. You could do that algebraically, but we're not going to do it. So the Gauss's method is partly restricting yourself to only 3 moves. And these 3 moves they're called row operations because they we think of each one of these equations as a row. So because eventually we'll put this in terms of other things called matrices, where we'll have rows in the matrix. These are called row operations. And this method, which is called Gauss's method, it's after a guy in the 1800s named Gauss. And he's the one who came up with it. So, okay, so there's 3 operations. They have names. There's the row combination operation. There's a swap, where I interchange 2 rows. And 3, there is, rescaling. This is sort of an unusual word, rescaling, because what you're thinking of is if you have a length and you sort of change its length, you think of that maybe the scale is like it's a word that's used in place of, you're changing its length, and it's like you're changing the scale at which it somehow, think of a scale as like a length scale or something like that, and you're changing its length. The problem, and so the reason for the term rescaling is that we're all dealing with real numbers. These could be any real numbers. Now, I've written these as integers, like 2, 5, 4, and 9, and we'll almost always stick with integers, but they're conformably real numbers, and sometimes we'll see fractions. But you could put like pi or some other number in here. There's no problem with that. However, you could also use, and we'll see this at the very end of the course, you could use complex numbers which have the square root of -1 or I in it. But you don't have to worry because we'll still only deal with integers. Okay, so but the word rescaling came in to include all these possibilities. Even though we're only going to see integers, the rescaling just means change the length. Okay, so what are these row operations? Well, the key idea here is this. The row operations aim to transform this problem into a simpler problem that we can solve more simply. And the idea is that you can prove or show that these 3 row operations they don't introduce any extra solutions and they don't lose any solutions. So if we want to find all the pairs of values, x and y, that make both these equations true, that's what a solution is. We're guaranteed both that these 3 operations will allow us to do that because they don't introduce any new solutions. You don't lose any old solutions. And so we're transforming this system into an equivalent system that has the same solution set. So instead of going straight for the answer, we're going to transform it into a simpler system. Now, let me show you each of these row operations on this system. So I'm going to copy the system down here. Now we could do we can transform this to a second system that is a equivalent system with, say, let's do a row combination operation first. Now, because the word row, we want to make a little notation for row operations, and it's based on the fact that the Greek letter row, which is spelled R-H-O, sounds like row. So we're just using this symbol because it sounds like row, okay? So we're going to use row to indicate a row operation. And what the first one is what I can do is I can multiply one row by a number and add it to another row. I don't change the row I'm multiplying. So here, what I can do is I can multiply the first row. This is row 1. This is row 2. So I'm using these indices to indicate which item is in the list in this row. So we're going to say, well, I can multiply this first row by -2, row 1, and add it to the second row. So this operation says multiply the first row by -2 and add it to the second row. Now, I'm not going to change the first row. I'm only going to change the second one. Only this changes. So this actually could be like minus row 1 plus row 2 equals row 2, but we'll leave off the row 2, and this is just a compact way of saying we're going to do the following operation. We're going to leave the first one alone, and we're going to add them term by term. So we're going to take -2 times x plus 2x. Well, that's -2x plus 2x is 0x, plus -2 times 2y is -4y, -4y plus 5y is just 1y, and -2 times 4 is -8, and -8 plus 9 is 1. So here's my new system. So it illustrates a row operation of multiplying one row by a number and adding it to another one. And this is part of the goal. What I've gotten here is, let me just with this 0 here, we don't have to write, we know that 0 times any number is 0. So this is the same thing as x plus 2y equals 4 and y equals 1. Well, this was actually our goal. This is called echelon form. No matter what system you get here, it's going to be another linear system, but this is the goal. The goal is to put our linear system in what's called echelon form. And it will guarantee that these 3 row operations will always allow us to get any linear system, no matter how many equations, no matter how many variables, into a linear system. And let me